Good morning, everybody, and thank you again for joining us today. My name is Bianca, and I'm the Outreach and Engagement Team Leader here with Master Builders. I'm delighted to welcome you all to today's webinar, which is the 7-Star Homes Construction Training. So before we start, Master Builders acknowledges the traditional custodians of country throughout Australia. We pay our respects to elders past and present, and we embrace our shared future. So before I hand over to my colleague Phil to introduce our presenter for the day, just a couple of housekeeping things for you. Firstly, as you know, this webinar is being recorded. We will make sure to email this webinar out to you following the session. And we ask that all questions be directed through the chat box down below, and we will be answering this as we go. So thank you again for joining us, and over to Phil to welcome our presenter.
Thanks very much, Bianca, and thanks very much for setting this up this morning. Good morning, everyone. This is our last and final presentation, for the time being at least anyway, on the training sessions we've been running across the state, and the webinar we ran last week, and this is the second part of that webinar, if you like, this morning. And this morning's webinar focuses on the construction part of moving from 6 to 7 stars. So tips and tricks for doing that and doing that effectively. We've got our presenter this morning, Sean Maxwell, who's from the Building Compliance Testers Association. Sean's been educating builders and project teams on building science in Australia since about 2016. And I think I've known you since about then, Sean. His passion is translating abstract topics of building science to practical solutions that builders can easily implement. He runs the Air Tightness Testing and Measurement Association in Australia, a group of professionals who share a passion for using the magic of the blower door to reveal hidden secrets about buildings. So he's making it sound very exciting there. He's got lots of tips and tricks and lots of practical solutions, as I said, just little things to look out for that will make a whole lot of difference to what you're doing. I just want to also acknowledge the support of Sustainability Victoria, who have provided the funding that's helped us deliver these programs around the state, and as to webinars in the last 2 weeks. So yeah, as Bianca said, if you can post your questions in the Q&A, Bianca, or the chat on the chat box.
Yep, just the Q&A at the bottom there.
Yeah, and I'll either jump in and interrupt Sean as he's going and try and get an answer for you, or we've got Grady Peterson from Sustainability Victoria on the line as well. We'll try and provide some answers for you as we go. So thanks very much, Sean. Over to you.
Awesome. Good morning, Phil, Grady, Bianca, and all of you. Glad to be with you. This, I think, is pretty exciting, going from 6 to 7 stars. It sounds a bit abstract sometimes, but it really, in some ways, will seem like a big leap, but in other ways, it's actually not that different. It's just an evolution of how we're doing things. So the stuff I want to talk to you about, I want to make this webinar interactive, and so please, question and answer would be really good. I'll try to go fast so that we can leave time for questions throughout, and I'll try to answer them as concisely as I can. All right, so let's make this interactive like this. So take your phone, take a screenshot, just use your camera on this QR code here. This is going to take you to a web page, which totally anonymous, totally secure. We don't care who exactly answers what, but this is just some ongoing polls so you guys can see how each other is feeling about things. We're going to ask some questions throughout. Don't worry if you can't get this right now, the QR code will show up again. It should work well. So scan that QR code and then just keep that link open on your Safari or Chrome or whatever your web browser is. On your phone, and you can participate in these polls as we go. Cool. So here's me in a picture of me doing a blower door test. I'm going to talk a lot about blower doors. That's this blower in a door over there. It's a fan. I'm the scheme manager for the Air Tightness Testing and Measurement Association. If you ever thought that there was a hopeless group of nerds that could be any more hopeless, this would be the one. ATMA is started in the UK, and now it's actually in like 10 countries, I think, have joined the scheme, because they've really done a lot to sort out how air tightness testing is done systematically And so what we want to do is I'll show you some of the things that we're learning through that. And I think it'll help Australia get through some of these challenges coming. All right, so quick first poll. Here we go. Take a screenshot of that QR code, and then you can participate. Just want to know, why are you guys here? Like, what are the main reasons that you are wanting to participate in this webinar? Let's see, we do have a question already, I see. Can you paste the? All right, we will paste the. So we have three answers coming in. See this little counter up here? It's telling me how active you guys are. So please just let us know, just get a sense from others. Why are you guys here? You want to know how to get from 6 stars to 7 stars. You want to get a competitive edge on on the market because you want to get to 6 to 7 stars before everyone else. Just let us know. All right. You can pick more than one. So let's see. Most people want to learn about energy efficiency. Some want to build more energy efficient homes. Many want to know what's coming in the NCC. Probably a lot of you already have a good idea of what's coming in the NCC. Many want to build, some want to build more comfortable homes, and let's see, not very many of you don't want to mess up our home planet. Just kidding. I know that if you're talking about your priorities, you definitely need to know what directly applies to your job. So, and CPD up to date, that's much less common. Interesting. So most of you want to learn about energy efficiency. Awesome. Let's get into it. So the contents of this workshop are that we're going to touch on what's in NCC 2022, how that's coming, and how that deals. We're going to deal with some thermal bridging and insulation issues. These are all things that sort of like the code says one thing, but then how you actually do that in real life, that's another thing. Some things in the NCC are related to condensation, which we're going to talk about how that's actually a risk that we can try to mitigate. We're going to talk about building more airtight and using basic ventilation so that build tight and ventilate right. And hopefully we're going to have more basic, we're going to have time for some questions and answer along the way. So let's jump into construction code. What's in the NCC 2022? And if you can tell from my accent, originally from America, so I have a perspective, and I recently went back to visit America and talked to my buddies there about how is the code there changing. And basically, I'm speaking to you from the future because a lot of the things that are in the codes in the US are starting to creep into codes here. For better or for worse, for you guys, there are things like double glazing is mandatory, basically in all of the US. Maybe not in Hawaii, but in every other climate, from warm climates like Florida, Texas, Louisiana to cold climates, it's just mandatory for a bunch of reasons. Energy savings is just one of them. Blower door testing is mandatory in many US states or municipalities. You can see, so a lot of this stuff, there's more testing, more verification of things. So not just blower door, but duct tightness testing. If you can believe that they actually test the ductwork for HVAC systems, your air handlers, you have to test the ductwork for air tightness because, well, simply you're paying to condition this air. You don't want the air squirting out of leaks everywhere before it gets to where it needs to get to. So you have to test the ductwork for air tightness. That may come to Australia someday. Other stuff, like there's basically, you're not allowed to have metal framing for your homes that isn't covered by continuous insulation because it's a thermal bridge and really hurts energy efficiency. So continuous insulation is how you do that. So these are some of the things that the US has implemented in their codes, which are probably coming to Australia soon. So I guess the message is that codes creep over time. They don't it might seem like some things come all of a sudden, like, geez, we didn't see this coming, but actually, believe it or not, the regulators are quite scared of upsetting the market or moving too fast. So you can, I would encourage you to get involved in codes discussions. They don't do this in a vacuum. They listen to the industry. So if you have concerns, get involved. If you look at the map of the US states, there's a patchwork of all these different colors. Those are all different versions of the International Energy Conservation Code that most of the US states have adopted. And so if you think about it, there's some states without even a color. Those are states without a statewide code. So individual cities might have, or counties might have a code, but not one for the whole state. So when I say the US building code, it's actually more like, it's sort of like 50 sets of building codes there, or actually even more than that. Like some municipalities like New York City has its own extra special code as well. So it's a patchwork, and Australia is the same way. So you'll see that in some things, we'll see a theme here that some stuff is sort of introduced into the code, and then it's made a little bit more stronger in the next version, and then a little bit more in the next version, and you can see where this is going. So we'll talk about examples of that. So here's another quick poll here. Main thing from the code for NCC 2022 is we're going from 6-star to 7-star, most likely. So what do you expect? What are the ways to get from 6 stars to 7 stars? Open that link up on your phone, scan that code, and participate. Just say, what do you think are going to be the ways that you're going to get from 6 stars to 7 stars? If you're not at 7 stars already, what do you think are the easiest ways or the ways that you're going to use to do that? Okay, let's see. So better orientation, air tightness, better insulation, better windows. Interesting. So better HVAC is also one. HVAC is going to be more of an important way of doing things in the future, because we're going not just from basically the current framework, which is fabric, pretty much fabric only approaches to energy efficiency for the NatHERS rating, to including HVAC as one of the whole of home components here. So most of you think more insulation, better orientation, better air tightness. Those would be the ways you get from 6 stars to 7 stars. Cool, interesting. And okay, cool. Next. So some of the changes planned for NCC 2022, like I said, going from 6 stars to 7 stars, it's just a general increase in stringency for air tightness, or for energy efficiency. But there's also some stuff in there related to condensation. So there's bits in there about when you're now going to need ventilation. If you build more airtight, you need ventilation. And there's changes to the materials you're allowed to use. So are there changes related to air tightness? Well, some of you said to get from 6 stars to 7 stars, you're going to use better air tightness. Well, not yet, really, because there in the NCC 2022, there really isn't anything in there about air tightness. So, but that's not to say that stuff isn't happening. I find this totally tantalizing prospects of using air tightness in your energy model to reflect how you build. So the way that this slide's a bit busy, but the software that you use to do a NatHERS rating currently just uses some defaults in there about how you build for air tightness. So they'd say you've got a bunch of downlights and they're close fitting or well sealed, stuff like that. That sort of check boxes of yes, it's been sealed or not, or it will be sealed. And that generates a default in there of maybe around 10 air changes per hour, or 10 cubic meters per hour per square meter. So doing that, using those defaults gets you to around 6 stars for a typical rating. But if you were able to change that, those assumptions to say, like a lot of you, if you've done blower door tests before, you'll know, well, actually, it's not that hard to get from 10 down to I regularly get down to 5s, to say. If you do that, then you're going to get almost a half a star better performance that you actually can't claim credit for right now, because NatHERS doesn't take air tightness directly into account. So this is something that Department of, actually, I'm not sure what they renamed their department now, was Department of Industry. They're now going to recognize that air tightness is a thing for energy efficiency. So you're going to be able to directly input the air tightness of your model. And then the way this works is it's like this. You will enter your air tightness into your model. You'll say, well, we plan to build our home to air tightness of 3. You put that into the model that then says, oh, actually, you get a half a star boost from going from defaults of 10 down to 3. So that means you can meet your star rating with that new influence, and then you can you actually have to then do that. You have to build tight and ventilate right. If you do this, the approach is going to require that if you use this thing in your energy model, you have to actually prove that you got to that point with a blower door. So if you say you're going to get to 3, you have to prove that you got to 3. And you also have to use some basic ventilation. When I say ventilation, hope that doesn't give you the jitters about how much that's going to cost and how complicated it's going to be. It's not that hard. Believe me, I'm fighting for you to make something that's sensible, easy to do, and also meets the objectives of indoor air quality and energy efficiency. So this is how it's going to work. Not yet set in stone at all. So first things would be that the software makers that had pictures of the logos up there, they're going to have to implement this into their software. That's in progress. So Hero has that in their software. Accurate has that in their software. First Rate 5 has that in their software as being able to use air tightness as a function. So basically, this is one thing that the government is seeing this as one way to sort of ease the transition from 6-star to 7-star eventually. Probably happening over the next couple of years for you to be able to use this as a lever in your energy model. So you normally couldn't use this lever before, but you will be able to soon. Not coming in NCC 2022, but sort of it'll be something that happens through NatHERS. So that's in progress. I find it very exciting because as the leader of ATMA, the Air Tightness Testing and Measurement Association, our group is made up of people who really, really care about building performance evaluation with a blower door. So the testers, people that go through the ATMA accreditation are accredited. They've gone through training. The data is checked by software. When you input it into the database, it scans it to make sure that it actually makes sense. The testers are audited. The market plays fair in that everyone contributes to the database. So they're all checking, basically is checking in all directions that things make sense. And what this does for the market for builders is basically starts to minimize the cost of testing for homes, because you've got now testers here. Here's a list of current testers in Australia, and there's more coming all the time. A couple others in progress of being certified right now that are doing these tests, and they're all basically playing on a level playing field. So this is going to drive the cost of testing down. So let's see, how will blower door test companies keep up with construction demand? The Department of Industry sees this not as something that's going to be a crazy out of hand demand, because it's actually going to go with the number of assessments that are done this way. So it's not going to become mandatory for using air tightness anytime soon. Probably not till NCC 2025 would be the earliest hope that blower door testing would be mandatory. The NatHERS path might happen sooner, but it's going to sort of be trickling on with individual homes that are doing this. So at the soonest, when I talk to them, the earliest that could happen is probably September, October of next year, that this would finally be available, an actual possibility. So how will APMA be able to cope with such an increase in demand? Well, we're growing all the time. So we have courses being scheduled continually throughout the year. And if you just look abroad, so in the UK, they have a couple hundred testers for a market similar in size to Australia. And this is working so well that they have done, it's required that 100% of every building that's built in the entire country of the UK has to do a blower door test, and they have to pass a target. So if you look at the average number of tests done per tester there, it's like, I think I heard the average was about 500 tests per tester per year. So if you just do some simple math, that means we don't need that many testers to actually serve this market, if that's what they're doing. And I'll just tell you, it was my first job out of high school, or out of college, was doing blower door testing for the Energy Star Homes program in the US. And I personally have done easily 1,000 blower door tests myself. So you do testing day after day. So young guys like I was, that was my first job. You just do testing, you crank them out. So it would be able to meet demand, I think, pretty well, as long as basically what we want from the government is a signal to know when is this going to happen for real, so we can just plan to make sure we have enough testers in place. So cool. All right. So let's talk about, we could talk about airtightness stuff all day long if I could, but I also will talk about thermal bridging and insulation, because that's also really important. Thermal bridging is, there's a basic example of thermal bridging. When I say thermal bridging, it's like a bridge for heat transfer to happen very quickly. Like, how does the heat get from one side of the wall to the other side? Well, if you have to go through insulation, it's going to be very slow. A thermal bridge is a bridge over that or through that insulation. It's going to take you there very quickly. So that's what thermal bridging is. It's just a thermal highway, you could say. So missing insulation has a massive, massive impact on heat transfer. How much of an impact? Like if this picture here is from a blower door test, where I just had my infrared camera there and I pointed up at the ceiling and said, oh, wow, look at those bright spots on the ceiling. Those are missing bats of insulation. And if you look there, they coincide here with a light fixture, smoke alarm, light fixture. So the installer must have thought, oh, I can't cover those with insulation because that's a fire risk. For some fixtures, that is. So how much of a risk is that? If you're missing a little bit of insulation, here's a hypothetical one. If you're missing a bit of insulation for those light fixtures, if you were to cover that insulation, if you had a light fixture that you could cover, if you were to cover that missing 10% of insulation with insulation now, would that save more energy than doubling the thickness of all the other insulation there? So if you're talking about bats of insulation, using one bag of extra insulation or using 9 more bags of insulation to cover the existing insulation, what's going to save more energy? What do you think? Real quick, do a poll here. What do you think is going to be saving more energy? Covering the missing insulation with so that 10% goes down to 2%, or doubling the thickness of all the insulation that's already there? What do you think is going to save more energy for a typical ceiling assembly? We've got 22 people eager to answer here. Awesome. So you get the point. Missing insulation is a massive, massive, massive penalty. That's just how the math works. It's I can work it out for you sometime. It's pretty crazy. Insulation this thick, which is thicker than I think any insulation I've ever seen in real life around here. You could add as much insulation as you want, and it's going to save less energy than just covering those little missing bits. So the missing bits are super important. So this picture of the missing insulation over these light fixtures, back then, this was 2016 that I took that picture. Back then, that might have been required for those fixtures that you couldn't cover them by insulation. These days, look at the box. All of them say, you should look for a fixture that says IC4 insulation. There's different insulation ratings. There's different ratings for the light fixtures. IC stands for insulation contact. Basically, you can cover the insulation, cover the light fixture with insulation, and it's not going to affect the longevity. It's not going to create a fire risk. These don't heat up nearly enough to cause a problem. So IC4 fixtures, you can just cover them with insulation. So if you took this picture again this year, hopefully this would look all purple, like all totally conditioned and no thermal bridging going on here, because you should just be able to put the insulation right over the light fixtures. That's how it should look in your, if you do an infrared scan of your projects, go ahead and cover them. Just look on the box. This fixture here is from Bunnings. You just look at the box and it'll say what the rating is. Most fixtures these days are IC4 rated, so you can just cover them with insulation. And if anyone has any questions about that, I'd love to learn more about light fixture ratings, but it should be pretty simple on that bit. Thermal bridging is also some basic stuff about missing insulation in some very common areas here. So you see this cold corner here? That's from missing insulation in that corner here. Where does that show up? How does that happen? Places like this. So at a corner here where framing is needed for structural reasons, there's this missing corner here where there's no insulation inside. And you might think, well, look, this side butts with this side and they're both insulated. So why do I need insulation in that corner? Turns out that's actually, those are the things that cause these cold corners. You wouldn't think it, but basically anywhere there's exterior wall, there should be insulation to cover that, because that's a big thermal bridge right there. That's going to harm the performance of this wall. So AS3999, the insulation standard for Australia, has ways to insulate these voids here. So this one you'd be doing from the outside. Once the framing's up, you'd go and tuck in properly cut bits of insulation in this this empty stud cavity there. Another one is to use what's called an open corner to turn the stud 90 degrees so that you can fit insulation behind it. So those are different ways of properly cutting and tucking in insulation in those missing corners, missing bits, and that will really help the performance of the assembly.
Beautiful. Sean, sorry to interrupt you. Just a reminder to everyone, we noticed that some questions are coming through Slido. Please direct them to our Q&A box down on the Zoom, just so we can monitor them from our end. Awesome. Thanks, Sean. Back to you.
Sorry, yeah, I didn't notice that. Actually can't see it. So thank you. All right. So here's some more quick pics of missing insulation here. Where the overhang comes, there's not much room to put insulation along here, but what you should do is use a high efficiency bat or a denser bat along here, around the corner. Actually, AS3999 AS3999 has illustrations of how you can use high density bats along the corner, along the edge, to make up for this gap here. Don't just not put insulation there, because it's going to really harm performance. So another example here is this steel beam here. Steel is very, very, very good at transferring heat, transferring energy. So to get rid of this massive thermal bridge, this is going to light up real bright with an infrared camera. You can use even a little bit of insulation, just a thin bit of foam board insulation along there to cut off that thermal highway from inside to outside. Some thermal bridges can can be so strong that they're actually locations for condensation, especially in humid environments. So these thermal bridges really have many drawbacks. So thermal bridging, it doesn't just have to be metal. Even timber framing has a big impact on this. This is accounted for directly in energy codes in the US, and I expect this to happen someday in Australia. So timber framing, when you talk about what is the insulation value in your wall, it's not just the value of the thickness of the insulation. It's not just R2 or R3 insulation that you're using in your wall. It's the timber actually is part of that assembly. It's part of the thermal performance. So just standard timber studs in a 90 millimeter wall, that presents a 15% loss in performance from the insulation R value. So it's 15% worse than R2 insulation, for example. Metal framing, though, is way different story. That same wall assembly is 50% worse than the insulation R value. So instead of, if you put R2 insulation in a wall and you're using metal studs, it actually behaves more like R1, which to me is just crazy how efficient these metal studs are at transferring heat between inside and outside. 1,200 times better at transferring heat than glass fiber insulation. So that's why in a lot of codes abroad, they require, if you use metal framing, you have to use some continuous insulation over it. So what does that look like? Stuff like this. So phenolic foam, mineral wool insulation, mineral fiber insulation, XPS, EPS insulation that goes over framing, that cuts off this thermal highway, and it's much, much better than just leaving bare framing. That's why it's required in a lot of building codes abroad. Someday, hint, hint, it'll probably be required here. So don't need to go too far into different kinds of insulation that are available, but expect that you're going to get more options here as time goes on. There's lots of different ways to do it. Closed cell, open cell spray foam are very widely used in the US. Definitely by far, glass fiber is still the most common insulation in the US, but they're using much more spray foam as well. So a combination of glass fiber and then continuous board insulation like XPS on the outside, super common assembly in the US. Expect similar stuff coming this way. So actually, sorry, before I get on to this, there are a couple quick questions here. What are the cost implications of a blower door test? Generally, I mean, the market rate for a basic blower door test for a lot of testers, if you just wanted to know if you're a builder and building many homes and you wanted to know how good are you doing right now, a lot of them would give you a complimentary blower door test because for the possibility that you might use them for all of your future projects. So ask, it's worth asking, I would say. But some of them, some of the blower door tests, market rate would be definitely less than $500 in a mature market, definitely less. So I think the average, it's common for a blower door test in the UK where it's required by code to be like, I think they said 180 pounds or something like that. So a couple $100, maybe $300 Australian. That's in the UK, and it's probably similar in the US. A couple ones, how can you target specific airtightness between 10 and passive house? In terms of knowing what practices will get you from 7 or 5 or 3, we'll talk about that. It's not that difficult to get from 10 to 5. Pretty much you do the things in this presentation, you'll get from 10 to 5. If you follow the building code, like actually follow it, you get from 10 to 5, I'd say. There's some simple things. We'll concentrate on the easy stuff first. Getting down to passive house, that's a whole other story, which we're not going to get into. Can blower door tests effectively be conducted before internal linings and fixtures? Absolutely. Passive house that really has, it's a standard that has really hard airtightness target. They require you to, they don't require, they encourage you. It's a really good idea to see how well are we doing before we cover everything up. Like, are we even close to getting our target? Because once you start putting internal linings on, it's really hard to find the leaks and fix them. So yes, absolutely. As soon as you have the windows in and the sarking on, some internal linings, as soon as you can get any pressure, you can go around and try to find leaks. It's as soon as you can do a blower door test, you should. In fact, a lot of builders will just buy a blower door for themselves and do it to see how they're doing along the way. So absolutely, testing it early is better. So I think cost involved for running a blower door test, again, we'll see how it shakes out here, but I would suspect that pretty soon the cost will definitely be below $500 for a standard blower door test. Not trying to tell the market what to do, but I'm just saying that's commonly what happened abroad. What's the cost of most most cost-effective method to insulate, being aware of the risks of EPS. Fire risks for homes, I'd say so fire risks of EPS, I'd say definitely is a concern for commercial construction. I think for residential construction, there's a lot of differences between commercial non-combustible construction and residential construction. There's lots of burnable things in residential construction, like timber framing, that is not allowed in non-combustible construction. So it's sort of different. So we'll leave that one for another presentation about types of insulation and fire risks. How can we insulate structural steel like I just invented a new word, square hollow sections, we'll call them squallow sections, in our current framework, using a thin board of XPS, EPS on the inside. Even if it's 10 mils thick, will do a lot to reduce that thermal bridge. So in that picture I showed of that steel lintel, steel beam over that big sliding door, that would do the trick. Thin board of insulation. Another one, question about fire insulation using EPS. Yeah, so EPS, XPS do have, they are combustible. So yeah, that's true. That's about all I'm going to devote to that question at the moment, because it's a big, long topic. A value of 10 to 20 millimeter air gaps between internal wall and external surface. Let me just tell you that that common practice of using an air gap to get some extra boost in insulation performance, it's actually explicitly not allowed in building codes abroad, because it is not nearly as much of a benefit as you've been told it is. You get a convection current happening in the wall cavity, where heat, it's just not a good idea. I will be fighting this battle with for many years in this country. It was fought 20 years ago, 30 years ago in America, and the gap doesn't help. The code specifically says to insulate the whole cavity, the entire thickness of the cavity, don't leave any gaps, because it actually has a detrimental performance for the insulation performance. So what star rating would a passive house be? I don't know, 3 million? I'm not sure. It's, I don't honestly know. It's maybe 8, 9 stars. It's not actually nearly as difficult as you think it might be to get to that level. So glazing, I'm not going to talk too much about this because it's not really a design thing, but just to know that your windows are going to have things that affect their energy efficiency. Like the biggest one for Australia right now is the leap from single glazing to double glazing. There's a big benefit from doing that. And then there's lots of other things. So the gas fill between the panes of glass, argon, krypton. If you didn't know that krypton was an actual thing, it's not just a Superman thing. They use it for super windows. Krypton gas between the panes of glass. The spacer, you can use a metal spacer or even a thermal break spacer between the glass. Lots of different things that will affect thermal performance of windows. The frame type also has a big impact on that. So the frame, aluminium is probably the worst performance in terms of thermal performance of the frame. Timber's better than that. Metal clad timber, more expensive version of timber, more expensive, more durable. UPVC is better than timber or aluminium, and then fiberglass is another option that's also quite good. So another question, is there expectation that moving forward, these items to achieve 7 stars are going to be regulated by inspections? I don't know. That is not, I would expect someday, yes, that's going to be, as-built verification is going to be a thing in real life. Would you nominate the equivalent R value of single and double glazing, excluding the frame? Can you nominate the equivalent R value? No, I can't personally. And there's so much that depends on that. It's a whole section of science to itself. But it's actually really important to include the performance of the frame as well. So that's why in the US, and so AFRC has ratings for the whole window assembly. So not just the glass, but the window frame as well. That's really the performance. It's the performance of the whole thing together. So the benefits of high performing windows obviously are reduced heat loss, but it also improves thermal comfort. People are going to be radiating less heat towards these cold surfaces, so they're going to feel better. Even in a passive house, you can have massive windows. Of course, they're massively expensive windows, but big windows. You can be sitting on the couch watching TV and feel totally comfortable, not feel cold. Right next to me, I have floor to ceiling glass here. In the winter, it gets pretty chilly in here with these because I'm radiating heat to the windows all the time. Single pane windows, not that comfortable. Double glazing also reduces noise transfer and reduces condensation potential, and that goes for the framing as well. The better performing framing, fiberglass, UPVC, is better at reducing avoiding condensation than aluminium, which is really good condensation surface. It's actually sort of ironically, it's sort of a dehumidifier in itself because so much condensation collects on it, it dehumidifies the air. So condensation, boo. This is a picture right in the Sydney area here where we got called to see why they were having so much condensation. Some basic stuff that we'll go over in this. So this is a picture from my last apartment when I lived in Bondi. Difference, I'll go over the main difference between that apartment and this apartment. So difference of 100 years in, when they were constructed, but that one's single pane glazing. This one's single pane glazing. That one is uninsulated masonry walls. This one is uninsulated masonry walls. Why do we get condensation in that building in Bondi where we don't get it here? Not because of the location, it's because of one very simple thing, ventilation, which I'll go over. So, okay, wake up, do a quick poll here. What do you think? Is increasing the energy efficiency of homes also going to increase the risk of condensation? What do you think? Are we in for a soggy awakening here? So many think it will increase the energy efficiency, will increase the risk of condensation. Some think no, it's not gonna. I'd say if I were to answer this along with you, I'd say it depends. Like, yes, I would say it does increase the risk of condensation, but there are ways to mitigate that risk. So if you use those methods of mitigating risk, it's actually not that scary. So we'll go over how to mitigate those risks. So actually, I just put this slide in here last night just to say, the way I'm thinking about this is there are ways to, there are risks for adding condensation. So building practices like moisture content of building materials has potential not just for condensation, but for rot of materials. So just some standard building practice construction processes, those have a risk. The enclosure design, how well you've designed your enclosure to be resistant to condensation buildup. Waterproofing, that's one thing that I think we need some major advancement here. Waterproofing of windows is a big one that I will go over here. Airtightness, I'll go over that. That's actually a condensation. It both increases condensation risk and decreases it if you also pair it with some basic ventilation. So I guess the reason I put insulation in there is that the more insulation you add, the more you retard heat transfer from inside to outside. So when people used to say, well, we never got problems with condensation until we added insulation, that's actually can be totally true. That when you add insulation, the thing that used to keep the building mold-free or condensation-free, or at least if condensation happened, it would dry out, is there's just tons of energy waste that was just drying that wall out all the time. So just pouring heat and pouring heat and pouring heat, and that would dry this building out. So adding insulation retards that heat transfer, reduces the drying potential, and you're gonna get increased moisture risk. So let's go over ways to mitigate these risks here. Moisture risks, that's the one thing that's enemy number one for buildings. It's like the most basic thing. You don't want rain falling on you while you're sleeping. Bulk water is the main moisture risk. Next, air leakage is a huge moisture risk that you can take some basic steps to mitigate that. And then vapor diffusion is one that the building code has started to address through materials choice. So we'll go over these in ways to how they're a risk and how we mitigate that. So in terms of importance, you'd say vapor diffusion. Let's just say that's a risk of one drop worth of risk. Well, there are studies and experiments to show that air leakage through like air leakage can have literally 100 times more moisture transport capacity than vapor diffusion through solid materials. And bulk water, I just picked a random number here. I said, yeah, it's like 1,000 times more important. You're definitely going to get, without proper bulk water management, you're 1,000 times more risk of moisture damage. So let's go over, let's start with that basic one first. Here's one that should be a no-brainer: material storage on your job sites, covering all your materials when they're not being accessed during construction. You actually can see the one board that's not under the plastic here. Maybe they use this one to keep it down because it's already warped. But the other materials here are elevated off of the ground with boards to lift them up from collecting rainwater. So this is bad practice here. A lot of these images are from Building America Solution Center, which is a free resource from America that has lots and lots and lots of good guides on basic energy efficient building practices. So they put this out to help the states deal with increased code stringency. So material storage, big one, because if you start with wet materials, that water has to dry out before the enclosure happens. So if you get yourself one of these things on the left, this is a moisture meter. I got one from Bunnings. It's right over here. It's got two pins that you poke into the timber, and you can see it's got to be less than 19-20% moisture content. Otherwise, just the biology of mold is that it's going to start digesting your building materials, your timber, above about 19% moisture content. So it's easy to check if you have moisture in your construction. Here's a job site in Queensland that was totally unprotected from rain. I understand that will happen during construction, but if you find that there's more moisture content, rent or buy a blower once you get the roof on to dry that place out before you put linings on. In fact, it's better to do that before you put insulation in, because again, the insulation prevents warming. So you want to dry that timber out before you enclose it. That should be a requirement. So when I was doing a blower door test, I had my infrared camera and I was thinking, I pointed at this corner here and I was like, ooh, look at this. Oh yeah, tantalizing. What's that very cold corner over there? Why is that lighting up so dark like that? Is there a major air leak? No air leak. What was going on? Well, I go over to the outside and I see, okay, look at that first course of bricks is totally soaked. And so it's clear that there's water getting, soaking that brick and possibly soaking the bottom plate of that wall. So why is that happening? If you look at the drains here for the site here, they are above the ground level and really at the level of the first course of bricks. The water has to pile up pretty high to get out of the drain. So it's clear this site drainage here is not good enough to dry this building out. I'm not saying that this is, if you think that this is not a problem, you just aren't looking around, because this was soon after I got here in Australia, and one of the first blower door tests I did and found this. It's a lot more common than you think, just some basic site drainage to make sure that these drain that out. So Brad Lawrence says, could that also be an air leak? I confirmed that it indeed was not an air leak because I went around and felt there no air leak. It's just the soaking from site drainage. You got lots more pictures of this site to show that there's evidence of silting and everything. So water is, after a heavy rainstorm, water piles up there and soaks the bottom plate here. Not a good idea. Not a good scene. So if you think air leakage is going to help dry your building out, it can often do the opposite. So this is sort of an extreme example here, but it will prove the point. So here's a swimming pool that had a very expensive HVAC system that they just couldn't get to work right, couldn't get the target humidity in the aquatic center where it needed to be. They did a blower door test. You can see the guy here wiping sweat from his forehead. It was so humid in there, condensation on these nice double pane windows here in Melbourne area. Why is this roof parapet lighting up like a billboard with infrared? Well, that's why. Opening up the parapet and look inside, stick your camera down there, and holy cow, they only use the cheap duct tape. I'm kidding. You shouldn't be using duct tape for air sealing, not like this. There is just massive amounts of air leakage. Down here is basically connected right to the pool area below. Just absolute pool level humidity in this assembly here. And there's basically no insulation in here. So no insulation and very poor air sealing. So there's just tons of air leakage coming through from below, going up into this parapet assembly and causing major condensation. So using the wrong materials here as well. This is a vapor permeable wrap in this assembly. That's not the right place to be using this, and it wasn't even sticking well. So not a good scene at all. Just literally buckets of condensation happening in this roof parapet, and this place is a year old and it's already getting mold and mildew up in this. There shouldn't be anything in there. So the food for this is just the dust that blows in from around, and with enough moisture, the fungus starts eating it. So air leakage is the source of this water vapor. So air leakage can carry major moisture risk, not just for a swimming pool, but for your own buildings as well. In Victoria, I've seen this many times. I mean, this picture is from Bendigo, I think, or Wodonga. There are evaporative coolers all over the place, and they're quite energy efficient. They use a bit of water and provide cheap cooling. Totally fine. But to avoid mold in your walls, you need to make sure that there's plenty of pressure relief. So these force humid air down into the building, and that needs a way to get out, a free path out. You don't want that humid air to be going into your wall assemblies, because it can collect there and then cause major damage. So pressure relief, that's by design, and then absolutely attend education about that. And they can't be lazy about it. Like they really do have to do it like it's designed. Need to open the windows so that has a place to go, not into the walls. In this case, it should be a code requirement. If you use evaporative coolers, you have to seal the heck out of the walls so that moisture can't get into the walls. You want it to be going out the windows, straight outside, provide that cooling and go outside, not collecting in your walls. So airtightness in this case would be a very good thing. If you're going to play with, not playing with fire, if you're going to play with water, know that it can soak you. Here's another bit about air leakage and energy and comfort. Most evaporative coolers get fitted with gravity dampers. They just force open under air pressure, and then they fall closed by gravity. But motorized dampers are required in the building code in the US, and hint, hint, will be required here in Australia someday, that if you use an evaporative cooler, it needs to have a motorized damper to force that damper closed, so there's not just gushing energy throughout the year. Every time the wind blows, those things can flap open and just waste lots of energy. So a gravity damper should be required by building code. Last perhaps most interesting way of vapor diffusion is straight through solid materials. I don't know if you realize this could happen, but water can go straight through a solid material like, well, this might be relatable. There's permeable materials like the Gore-Tex jacket on the right can let water vapor like perspiration through, whereas impermeable ones like the plastic one on the left cannot let or very slow at letting moisture vapor through. So water vapor, those individual molecules of water can pass through solid materials through tiny, tiny little gaps. And that happens more in some materials than others. So for building code, there's a standard for this. It's called AS 4200.1, AS 4200.1, and that has a classification for these materials. So class 1, class 2, class 3, class 4. Class 3 and class 4 are permeable. Class 1 or 2 are impermeable. And so you can make something that's semi-permeable or impermeable. You can make it more permeable by poking little holes in it. If you look real close here, you can see little holes poked in the membrane here by manufacturing process. That's how they make it more permeable. They poke holes into it. So when you poke holes into this foil membrane, it lets a little more water vapor out. One way of achieving that end. Other way of doing it is by making a fabric material. This is basically how the rest of the world does this, is use a material that lets water vapor pass through it. It doesn't have to be a new plastic thing. In the US, it's very common to use, or at least it was common to use, building paper, which is a paper that's impregnated with asphalt. And that actually lets water vapor molecules pass through, much like a Gore-Tex jacket for your house. So these little metrics here, micrograms per Newton second. I know you guys all think of it in terms of micrograms per Newton second, but just luckily it says on this on the membrane packaging what class it is. Class 3, class 4 is vapor permeable. Let's talk about how this matters for you. So NCC 2019 says in climate zone 6, 7, and 8, which is Melbourne among them, you need a class 3 or class 4 membrane. So it says vapor permeable. Those are class 3 or class 4 membranes, or climate zone 6, 7, and 8. Now, remember I said codes creep? So, all right, we start with class 3 or class 4 in climate zone 6, 7, and 8. 6, 7, and 8, you can use class 3 or class 4. In 2022, it says, well, climate zone 6, 7, and 8, now you can only use class 4. You can't use class 3 in those climate zones anymore. So that one, the foil membrane with the holes poked in it, you can't use it in climate zones 6, 7, and 8. So you need to use, in climate zones 4 and 5, you can use a class 3 membrane. Can you use a class 4? Yes. It needs to be at least as permeable as class 3. Class 4 is more permeable. So starting in NCC 2022, wraps have to be more permeable and in more climate zones. So remember I said codes creep? Know that these sorts of requirements are coming, and they're just going to get more widespread over time, because that's the way the science should lead us, and that's how it's going to go long term. So what does this mean for typical practice here? So in climate zone 6, 7, and 8, which are these blue areas, which is most of the state of Victoria, you should be using class 4 membrane only, like one of these fabrics here, class 4 only. And in climate zones 4 and 5, you can use a class 3 or class 4. So those two. Nowhere should you be using a class 1 or class 2. So sometimes you'll see material packaging that says stuff like this. This product complies with AS 4200.1 and therefore meets all requirements of the National Construction Code of Australia for insulation and sarking type materials. But if it's only a class 3 product, that means that for most of Victoria, it's not actually going to be allowed for most of the state. So even though it says it on the package, you got to check the labels. Here's where what it says on the label. I just took these pictures in a Bunnings. It says right in there, vapor classification. And this is a class 4 membrane. It is vapor permeable. So the class is right on it. AS 4200.1 has this labeling requirements. So just looking on the shelf in Bunnings, you can see they have some class 2 ones, class 3 ones, class 4 ones. So some of them are going to be usable in most of Victoria and some are not. So check the classification. So this is, again, here's the shelf in Bunnings where there's some class 4 membranes there, which these wraps here, all these requirements that I'm talking about here are for wall membranes, not talking about ceiling membranes. In fact, you can see in this picture here, so this one's wrapped on the wall here, this one's wrapped in the ceiling. So can you buy these? Absolutely. Could you use them in a roof? Absolutely. If it's class 2 or class 3, yes. Those requirements I'm talking to you about are for walls only. So here's a quick quiz for NCC 2022. Where in Victoria is it okay to use a class 1 or class 2 standard foil sarking in the walls of a home? Where can you use a class 1 or class 2 membrane? 2 smart people, 4 smart people, 7 smart people, 10. All right. So most of you have the right idea. Class 1 or class 2, one that says impermeable or vapor barrier on that label, nowhere in Victoria, nowhere in the state of Victoria can you use one of those foils in the walls of a home. Nowhere in Victoria. In Mildura, that's climate zone 5, I think, you can use a class 3. It's still got to be permeable, but it can't be a class 1 or class 2 standard foil. So nowhere in Victoria can you use a class 1 or class 2 in the walls of a home for NCC 2022. Know that. Don't get stung by this, because if someone's looking and you've used the wrong thing, they might make you take it off. Cool. So let's talk about, that was a lot about vapor permeance and just the wall wraps that you use. Just know this is going to become more of a thing as we go along. Now I'm going to go on my build tight and ventilate right crusade here. Building more airtight, it's not that hard. Here's some videos on YouTube that were funded by the government. They're pretty digestible 6-minute things about what are the basics of airtightness, like what are we talking about, what does a blower door actually do, how do you do a quick plan review with a red pen to outline where the air barrier is on your product to know what are the things you're going to have to focus on, and then how do you build that into a better seal, like with some basic window flashing and stuff. All this stuff is like the basics, 1, 2, 3 for how you get from 10, a permeability of 10, which could be considered typical or standard, down to a permeability of 5. So I just saw a question. Is that requirement for vapor permeability the same for roof sarking? No, it is not. It's not in that. There's nothing in the roof section for that. It's only for the walls that you can use, that you need to use vapor permeable materials in all of Victoria. So not class 1 or class 2, got to be class 4 in most of Victoria and class 3 in some of the colder parts, drier parts, just for the walls. Okay, so when you do an airtightness test, what does it mean? Let's do an imaginary one right here. We put the blower door in the front door, sucks on the house and puts a negative pressure there, and air leaks in to replace that air that's going out from the blower door. So that's where that comes in. That's how a blower door does it. It treats all leaks equally. Same pressure across the whole house. So anyone take a guess what parts of the building are actually tested by a blower door? Is it testing the walls, the doors, the windows, the ceiling, the floors? Is it testing the airtightness of the plumbing or the lights or the wall bordering the garage? Please take some guesses here. What do you think? what's it? What are we testing here? So fewer of you think that plumbing is actually being tested, and maybe the wording should be more precise. The plumbing itself is not usually being tested for airtightness, but definitely the plumbing penetrations are. Same thing with well, actually not the same with HVAC. I'll go over this point here in a second. So thanks for these answers. Yes, absolutely. Walls and ceiling, those are the things obviously we think of first with a blower door. The floors, maybe less, but yes, indeed, the floors can leak. Do it on an existing building, on timber piers, and you'll see the floor itself leaks. It's like the stuff for horror movies. If you use a fog machine under a house, you'll see the fog leaking up through the floorboards. It's so cool. So floors can leak, absolutely. The wall bordering the garage, if it leaks, it's going to measure it, man, and you'll see that. And it's not good smells coming from the garage. So when you use a blower door, thanks for participating in those polls. We're giving them to Sustainability Victoria just to see, so they have an idea what they need to focus on. So what's evaluated with an airtightness test? Well, really everything that can leak will leak with a blower door. So, and it includes lots of things that you might not think of. So up here, these light fixtures, along here, these electrical penetrations, it's leaking into this drop ceiling here and then up into the roof cavity there. The penetrations of the HVAC, the connections of the ductwork to the register, the register seal to the ceiling, that all leaks, and it will be measured. Obviously, all the penetrations through the doors and windows will as well. But then even the ductwork itself can leak. If the ductwork leaks throughout its entire life, that ductwork is going to be wasting building energy, not just when it's running, but also when it's off. It's just going to be leaking building air. So other things you might not think of, like stuff that's in the basement, it leaks into the basement, and then from the basement leaks up into the house and then out through the ceiling. You have to think of a house as a system. So yes, the walls, ceilings, and floors are leaking and going to be measured, obviously, so are the doors and windows, but plumbing penetrations, electrical penetrations, and then separations from the garage, the basement, those are leakage surfaces, leakage boundaries that get evaluated with the blower door. And the HVAC itself leaks. So when we're talking about airtightness, what is a good result? Like, let's talk numbers for a second here. So Sustainability Victoria says for the 7-star homes program, you need to get an airtightness of 10 or better. Lower is better. So 10 or less is required. In their zero net carbon homes program, they said you need to get to 6 or less. And all of them that went through that got to that level. So where does the number 10 come from? Well, in NCC 2019, if you use a blower door to prove that you comply with the building code, then you have to get less than 10 to prove that you comply. Green Star Homes, which is a standard, recently released standard for better than code homes. They say in climate zones 1, 2, 3, 4, and 6, you need 7 or less, and in climate zones 5, 7, and 8, you need 5 or less. So that's 5 is twice as good as 10. But is that actually difficult in the grand scheme of things? US climate codes for all climates similar to Victoria's, you need to get to 3 or less. And I hear from my little code birdie told me in the US that that's very likely in their next code revision going down to 2 or less. That's building code. That means you can't get your certificate of occupancy unless you get to 2 or less. So that tells you 2 things. First of all, is it that hard? Probably not if they can require it in building code, because if it were too hard, then the building industry would rebel. It's not that hard. And 2, the risks of doing that are not that much. They wouldn't require it in the building code. It's like building code is basically a risk reduction rule book. So they wouldn't require it if it were that risky. So there must not be that anything that bad about getting down to 2. Passive house, 0.6. Passive house is a world best practice of how to build energy efficient. I would absolutely aspire to be building that way eventually. So they require an air tightness of 0.6 or less. So that is definitely harder to do, especially for a first timer. But passive house builders regularly crank these things out. It's actually pretty much building code in parts of Europe to build that that tight. So we are on the left at 10, and we're saying building code in America is 2. So we got some road ahead of us. So I'm just curious, have any of you seen a blower door test before? Real quick, just let me know. Have you seen one of these before? And was it, if you saw it, was it tight? Did you see when it was very leaky? New construction, existing buildings, if you have seen tight ones and leaky ones, you can answer twice. So most of you haven't seen one of these before. So my advice to you is to get one done on your next project, just because there's opportunities in the future for this. It's probably going to be in the building code in the future. It's just a good idea to get to know as soon as possible what are some of the easiest things you can do to get better. It doesn't cost that much, doesn't hurt that much. It's just better to know. So it's like stepping on the scale every once in a while to know how much you weigh, just to get an idea. Okay, so most of you haven't seen one yet, but I expect that in a few years that number will flip. So when you see a blower door test, you turn yourself into a leak detective. It's pretty fun. You can use all sorts of things. Soap bubbles on the left here. You can use plastic bags. The shittiest of buildings use single ply toilet paper. Here, it's just, these leaks are so big that you can just, toilet paper just gets sucked into these holes here. It's kind of crazy. And then you can use fog to pretty dramatic effect. Infrared cameras along with the blower door, perfect combo. Either one alone won't tell you, but the combination of them is really powerful. Yes, you can use candles, but I wouldn't. Fire safety risk. And then if you have a guy named Harry on your job site, you can ask for his arm, and that's a really good leak detection tool. So is little whiskers on your chin. So you turn yourself into a leak detective with whatever you have at hand. Just a scrap of paper, a scrap of plastic bag. This door to the garage, again, that door, you might not think of that as outside because it's, covered, it will never get wet in there, but that is a major leakage pathway that is required by building code to seal that. So that's a missing air sealing accessory there, like a door seal that's missing. So you can start to get a handle on what are the things that are causing you the most grief. When we're talking about this, I'll talk about wall air barriers, floor air barriers, and ceiling air barriers. And air barrier assembly, that's like, I'll try to refrain from too much terminology here, but with a blower door, it's really eye-opening when you see this for the first time. You turn yourself into a leak detective. You walk around, you can feel with your own hands what's leaking, what's not, what works and what doesn't. So here under negative pressure, they're sucking, they can feel air sucking in around these windows here. So you can shoot fog at this window here and see the fog creeping in through the window itself. So in this case, this is a poor window component. The window itself is doing the leaking. There's a seal along here to the brick, so that's not leaking. It's the window itself, a poor component through your window assembly, or through your wall assembly. But here, there's caulk on the left, no caulk on the right. And the tester said, oh, geez, look at this. Tells me that's a lazy builder here. But the builder said, well, technically, the building code says that if the gap is less than 3 millimeters, that's close fitting and you don't need to use caulk. Well, you could call that builder either lazy or crafty. But they might be right. That maybe they don't need caulk there, but is that why there's fog leaking out through here? Is that the problem, that there's no caulk there? I'd say no. So if you see with the blower door, there's fog leaking out of this gap here along between the window and the brick. Why is that happening? Well, it's because if you go back in time, you'd look behind this and you'd say, well, there's no wall sarking there at all. So it's absolutely possible to do, build a wall without sarking. But brick itself is not airtight. It's never going to be airtight. One of the beautiful things about it is that it can basically dry out, and it's quite permeable to air, and so are all the mortar joints. So this is what a house like that looks like from the inside. If you were to take this wall assembly before you put the bricks up and then put some basic sarking there, that becomes a basic wall air barrier assembly. An air barrier assembly is the materials like the sarking, then the accessories like the tapes, and the components like the window. Those are all the bits. And to make it into a complete wall air barrier assembly, you seal it at the wall bottom plate. For a single story building, this is basic wall air barrier. To get from 10 to 5, do this. Use your sarking, tape the sarking well. Tape it at every successive course, tape it at all the penetrations, seal it at the top plate and the bottom plate. Then whether you include if you have a brick or no brick, it's basically not going to matter. If there's caulking or no caulking, it's not going to matter because the air is going to get stopped before it even gets to that joint. That is an effective wall air barrier assembly. Just watch some YouTube about walls. It's like, this is just, it's basically been standard practice in the rest of the world for 20, 30 years. So, and it's not that hard to do this really well. This, I'll plug this installation guide from ProClima. It's really good procedure of how you get good tension on your wall membranes to make them really solid and get a good seal with very basic and cheap processes. So using caulk along the bottom plate here, and then a stapling pattern here. So staple at the start and finish of this run of sarking, pull tension, staple, and then pull tension down towards the bottom, staple, pull, and these corners, staple, and then staple again along each stud. You'll get a really solid, strong membrane that then you can use good quality tape that will stick forever. So, and here's how to detail some basic detailing around the windowsill. All this stuff is super basic and not that hard to do. So that's a good free guide that's available, and there's tons more like it. So I would also suggest when you do a blower door test, if you're looking to see how well you're doing, do what this guy's doing. Does it look like a good idea? He's spraying water at his wall. What's going on? Is that, oh, this is one of those videos we did. So spraying at this wall assembly here, which this is a very typical detail here where the sarking is just cut flush with the edge of the rough opening here, and then you spray it with water and a light breeze and it just gushes in. So with the video, you can see the water pouring in. That's what will happen during a decent rainstorm. You get water just pouring into the wall. The more insulation you add, the slower that's going to dry out. And when I said that's typical, if you didn't believe me, there's just lots of pictures to prove it. This is just absolutely standard practice. By the way, this particular house here got a permeability of 5. So I'm not saying that this is good, but I'm saying some basic stuff that you can do will get you. Actually, I shouldn't even told you that because you'll think that this is adequate. This is early in construction. They're not done yet. And some things here, I would say this is not good. This is the cheapest tape ever, apparently. Even after a couple of days of installation, it's already peeling off. No sealing along the bottom plate here, sealing from the wall sarking to the damp-proof course. It's not sealed. There's lots of things that is pretty much as bad as you can get. not good. So even AS 4200.2, the membrane standard says, has a basic installation process for installing of sarkings to make a more weatherproof wall enclosure, and then to get the connection between the window component and the wall assembly, you do this. So use some basic sarking, flashing procedure here. Like I said, this is not rocket science, it's building science. Here are some basic procedure to seal that window component to the wall assembly, and you spray that with water and high pressure, and you just won't get air coming through. That's what you want your house to do, is to not get wet. So some pretty basic things, not that hard. So here's a couple links. If you want, just email me and I'll send you so much more. There's Matt Reisinger is a good resource on YouTube for awesome building science videos, or just basic build practice videos. Another one is Pro Tradecraft. I should put that link on here. Instagram account Building Science Fight Club has fantastic critiques on building weatherproofing details. Even Australian Glass and Window Association has a basic video on sealing against water leakage. So when I'm talking about air leakage, I'd actually say seal from the air seal from the outside in, like seal against water leakage first and then concentrate on air leakage, because water is absolutely the bigger boogeyman. So once you do a water seal, it's easy to do an air seal. Glass fiber, however, doesn't stop air movement. A basic, buy one of these foam guns and take care of it. You'll have it for many years. You can get a nice clean bead. This is not the cleanest, most artful bead of continuous foam around here. Buy low expansion foam that, so it doesn't balloon out of there, but get a can of foam. Don't buy the single-use ones with the straw that you get from Mitre 10. Buy an actual gun and then take care of it, and you'll have it for a long time. I had mine for many years. So one foam to trace around, do one pass around with each of the windows. You'll do a lot to get towards your air tightness target. That's another cheap thing that you can do. Like a couple cans of foam will get you, knock a couple numbers off of that air tightness result. At the bottom of the wall, seal the wall membrane to the damp-proof course. Then to make that, here's an example here. This is from the US, where they're using rigid sarking, like plywood OSB, plywood sheathing there. But you can just tape the wall plate to the damp-proof course, and then tape your membrane to the damp-proof course as well. Another cheap one that we need in this country is something like Dow Sill Seal, which is just a roll of foam that you roll this one. It's like $50 for $100 for 2 rolls, and this will do your whole house, where you run this around the perimeter and then set your bottom plates on top of it. That squeezes this foam bit and then makes a perfectly adequate capillary break, so that it's not going to soak water up, and we'll make a basic done air seal along the bottom plate. Then you tape your wall membrane to the bottom plate, air seal along the bottom, done. So someone says, are polyester bats suitable in lieu of expandifoam around windows? Definitely not. So polyester fiberglass just doesn't stop air movement. It's about as effective as an air filter as a cigarette filter. It just does not stop air movement at all. So, and I got pictures to prove it. I'll show you some in a minute. Is expandifoam between studs and window frames a better solution to sealing the air gaps than tape? Better. It's definitely cheaper. Absolutely. The good tape is not cheap. I'd say the good tape is, I would advise you to do that for waterproofing reasons. I think it should be absolutely required by building code. So do it for that reason. But then for an additional seal on the inside, the expanded foam for basic levels of airtightness would be totally fine. If you're going for passive house, then you probably need to have that extra tape seal, but a basic one for building code compliance, the expanding foam is going to be totally fine. What about the blue termite barrier under the bottom plate? I'm not actually sure what the blue termite barrier is. If you're talking about this Dow seal, maybe if we get a chance, I can ask you exactly what you're referring to. Sorry. Can the Dow seal be used in conjunction with the termite barrier? I bet. Clearly, we have some people who've seen a termite before. I don't know. Let's look at it. So that's one that I can just say, sorry, I don't know. So just curious, do tapes and sealants, do you use tapes and sealants on your exterior wall wraps? Always, sometimes, or never? Just curious. A couple of people say always, some say sometimes. In the past, I've had a couple of people say never used it. So, and I should say, I mean, there's more to ask there, not just on exterior wall wrap, but say around the doors and windows. Maybe do you use them along successive courses of membrane? Maybe do you use them on the top and bottom plate? There's lots of places to use tape. So I suppose it's a bit of a general question to say, do you use any tapes? But apparently most of you always do use some tape, which is good to see. Cool, thanks. You can keep replying to that. And now another bit about cordon termite protection over the top. Gosh, we've got a lot of conversation about termite barriers, and I have to say I need to do more research on it. So sorry I can't answer any termite questions. This is a bit where I need to educate myself. Maybe we can talk about it after. All right, ceiling air barrier. To get your wall air barrier to connect to the ceiling air barrier, in passive house, you would use a special membrane along the ceiling to provide an air barrier. In fact, in building codes in the US, for example, you're supposed to use a vapor barrier in a lot of the colder climates to prevent indoor air from getting up into the roof space. Here, it's not required yet. But how do you could do this with a just plasterboard. So what's the why is this a problem? So here's for a blower door test. Here, there's air leaking from this window, from this cabinet over the range hood. From the cabinet, not the range hood. If it was the range hood itself, you'd say, maybe there's a missing backdraft damper, non-return damper on this range hood termination, but that's not what's leaking in this picture. It's the cabinet itself. There's no, when you shoot fog, and then they had one person up in the roof space where they shot fog at this with the blower door running, and they say, so there's fog leaking up from, there's the duct for the range hood going out here. What's missing here? There's no ceiling air barrier assembly keeping that fog. You could say steam from the cooking pasta, or fog from the blower door, from the fog machine. That vapor is getting up into the ceiling space, into the roof space. There's no ceiling air barrier installed there. How do you fix that? It's a very common situation. You can do it pretty cheap and simple. Make a ceiling air barrier where there was none before with cheap and readily available materials. So let's go over some examples. Again, Building America Solution Center, lots of free resources, lots of pictures of bad, sad face and happy, good face. So we've got plasterboard here installed before the framing for this dropped soffit. Before that's installed, plasterboard installed above that, and then the framing is installed underneath, from underneath, and screwed through that. So a cheap, already available material, plasterboard, can cancel this problem. It's just not a problem anymore with something as cheap as plasterboard. There's lots of examples for what you can use. So building wrap, you could use a length of extra building wrap that's lying around. Tape that over this soffit before you put it up. Plasterboard, OSB, plywood, thin plywood, foam board. There's lots of things to just block this off. And then whatever business you have going on down here, it doesn't matter. So here's a good video. These slides I think will be shared by Master Builders. I think this recording will be shared as well. So that YouTube video on drop soffit air barrier, this is totally building code in the US. It's like explicitly mentioned that this should be standard practice. It's not that hard or expensive. So when I said that fiberglass doesn't stop air movement, here's proof. So if you do a retrofit, you'll see this stuff. See this brown fiberglass here? Why is it brown? It's because over the life of this building here, air has been passing through this glass fiber insulation and leaving the dirt that it carries with it as it goes. So you can tell that this was a problem by the dirt that's left behind. It leaves traces of how air has been moving. So to deal with this, in this case, they're using some paintable air barrier material. You can use foam here. Here's some other pictures here. This top plate, again, dirty fiberglass telling the tale of air movement over time. Air leakage leaves the dust as it passes. And then to fix that, you just hit that top plate with spray foam gun. There's a guy trying to creep out of the picture over there. The poor guy in the suit who brushes the fiberglass away, does the air sealing along the top. This should be absolutely standard before you add insulation for a retrofit. Air seal first. It's required in the weatherization program in the US. Required to use to seal before you insulate, because otherwise humid air from inside can carry that humidity up to the roof space and then leave it there. Again, totally sealing the ceiling is just totally standard practice, should be here too. So sealing along the top plates are your weak point here, because there's lots of joints going on between the top plate and plasterboard. Plasterboard itself is very airtight, but where it joins the top plate is not. So dealing with it on a retrofit situation is how you deal with it. For a new construction, your wall air barrier joins the ceiling air barrier. If your ceiling air barrier is your plasterboard, wall air barrier joins at the top plate here. So let's look at that connection more. So your wall air barrier obviously joins to the floor air barrier. That's what I was telling you about, taping the wall to the damp-proof course or to the bottom plate, and then tape the bottom plate to the damp-proof course, and then make a sill seal underneath here. You can use caulk if you want. If you don't like the roll insulation underneath there. So that connection between floor and wall, done. Now from the wall, you can use the timber itself becomes part of the air barrier, like this. So your wall membrane goes up the outside here and then gets taped to the top plate. The top plate then, if you're drawing a red line here where the air barrier is, that wood becomes part of the air barrier. Then that part of the air barrier then connects to the plasterboard. That is part of the air barrier. Then that connects to the next top plate, et cetera, et cetera, et cetera. So all these connections here, the wall is connected to the top plate is connected to the ceiling plasterboard. And the ceiling plasterboard can be a pretty decent air barrier. Again, this is gonna get you from 10 to 5 for sure. This sort of stuff, it's very, very, very little cost. So to make that wall connect to the top plate, you can do it a couple different ways. Put a bead of sealant before you put your plasterboard up. That cuts off any air leakage from this wall cavity into the top plate if the top plate is continuous. And then if you had a butt joint between two bits of top plate, hit that joint with a bead of sealant at the joint, like along here. You could, here's another application for that Dow sill seal. They drape this over the top plate. And then from below, you put the plasterboard up underneath that, and that presses against the sill seal and makes a decent, cheapo ceiling air barrier from your wall connected to the wall connected to the ceiling, and then ceiling connected to ceiling to connect to the ceiling, et cetera, et cetera, et cetera. So this is cheap, a way of doing this. Make a continuous ceiling air barrier. Basically, air barrier here is plasterboard and foam strip here throughout the whole house. So if you, with during your first blower door test and your budding leak detective, you use a bit of plastic to say, why are the power points leaking? We're in the middle of the house. This is not anywhere near the outside. I thought we were testing exterior air tightness. Why is that leaking? Well, if you look from above, you'd say, here, all the ceiling light fixtures, those are obviously leakage points into the living space below, but the top plates themselves can be leakage points as well. Everywhere that surfaces penetrate through the top plate down into the wall, that travels down and serves those power points with air leakage. So again, dealing with this, pretty easy with caulk or expandifoam. Hit each of those, just walk around one time, hit each of them, everyone you can find, hit it with the foam gun, and in 20 minutes you can be done with that problem. Another good video here about top plate sealing. So here's another one. This one's a sort of a special, especially fun, annoying problem. This cavity slider, it's so much leakage that this thing, during a blower door test, there was so much air leakage coming from this crack here that it was pushing the door out of the pocket, and it's just insane amounts leaking here. So check it out. It's just screaming out here. So how do you deal with this?
Still working.
Oh my goodness, my phone is talking to me. Taking this video from Bunnings Hume Doors, distributes through Bunnings, and taking the video there and saying, how are you going to make this into an effective, how are you going to stop that problem? It's easy. With a bit of caulk around that enclosure, along this dotted line here, put a fat bead of caulk there before the plasterboard is installed, or compressed foam gasket along here. That makes that into a little sealed box. And then any business that goes on here doesn't make it up into the ceiling space. Here's from Positive Footprints, some images of how they've done it on a past project. They just enclose the sliding door, the cavity slider, with a bit of thin plasterboard. You could use some extra vapor permeable wall sarking there. There's lots of things you could use to cut that leakage off before it gets up into the roof space. Doesn't have to be that difficult. Here, these videos are funded by Sustainability Victoria, and these are awesome, really sensible ways of dealing with some basic everyday problems. So using a plasterboard at the ceiling for your air barrier, using a compressed foam gasket along a cavity slider here. These are, again, basic things, not that difficult to deal with some basic stuff. Just check out Sustainability Victoria's website, ask Grady for the link, and it'll be in this, if you just Google on YouTube, Sustainability Victoria, you'll find it as well. Really great videos about some really essentials for making an air barrier at your ceiling with almost no extra cost, using expandifoam around doors and windows. So you can see light coming in here. That light's going to go away as soon as the foam is added around this enclosure, around this opening here. Not that difficult, easy stuff. Now, once you get all the stuff I've been talking about here is pretty much for single story construction. For double story construction or higher, it gets a little bit more work, but again, some basic stuff. So I walked out here, this house under construction. I looked up and it was like, oh geez, look at that. If you were an air leak, you could just travel right through the insulation, stealing its heat, and into the living space, feeding the power points and wall skirting in this room above, just make it totally leaky. So how do you fix that? Easy. That air leakage is coming through there now, but just cut to fit do a better job than I did with my little computer cursor here. Cut some foam board to fit that gap, and then seal around that with spray foam. You know, maybe it would take half an hour for someone to cut these bits of foam board along there and then hit that with a foam gun. Problem canceled. The sarking here leaves, installation here leaves something to be admired, but that can be improved as well. But at least these big gaps here can make that a non-issue pretty cheap and easy. You could use foam board, you could use plasterboard, you could use lots of things, anything that's going to stay there durably long term. So cheap ways to get down from to 5, like I said, so you can get that extra half star for very little cost. Use a good membrane wall wrap on the exterior, good quality, one that's going to last, one that's I would recommend one that is going to hold up against long-term UV, one that's going to hold up against long-term temperature stresses on it. So use a good quality one. Tape that seal to the top and bottom plate, tape it to the windows, make a good weatherproof seal around the windows. That should just be absolute standard practice to make weatherproof wall assemblies. Also extend that wrap to separate the garage from the living space. So isolate that garage from the living space. Normally, I mean, if you think of sarking as therefore weatherproofing on the exterior, you can also think of it as a basic air barrier between the living space and the garage. So it can provide a pretty decent air barrier. Just another couple strips of sarking there to separate the garage from the living space. Cheap and easy. Seal around the windows on the inside with a foam gun. You shouldn't not do that unless you have something better, but that's, I think, absolute minimum, easy one. Use material above drop ceilings and soffits to isolate those from the living space below. Do that in the kitchen and the bathroom. That's an easy one. Don't use building cavities as ductwork. Do I have a special slide on this? It's actually explicitly prohibited in the US building code. Has been since, 2009 or 2012 to not use a building cavity as a ducted return. It doesn't work. Block big bypasses between floors, like with those foam boards. That was this previous slide. Use a ducted bath fan. This is in NCC 2022 already. Use a ducted bath fan and range hood, and then have good draft stopper at the end of those. Use IC rated light fixtures. Should be standard already, but just check the label to make sure that's IC4 rated light fixture, and then seal every penetration you see, and you'll be sweet. So we talked about build tight. Let's do a real quick recap on ventilate right. Holy cow, I'm going way over time here. All right, what kind of ventilation do you use in your projects? You can answer this if you want. I'm going to skip for interest of time here. For different types of ventilation system, we can talk about balanced and unbalanced ventilation. So exhaust dominant ventilation and a supply dominant ventilation, they push air in or they pull air out only. Those are unbalanced. Balanced ventilation is like an HRV where you take equal parts of air in and push them out. So 100 liters in, 100 liters out, that's balanced. Supply pushes 100 liters in, exhaust pulls 100 liters out, and is not directly replaced by air. So where does that air come from? And where does each of these things best use, and what can go wrong with them? Well, balanced ventilation is highest first cost because it has 2 sets of fans, 2 sets of ductwork for intake and out exhaust. It has higher maintenance costs because it has to have filters. It's really only best used for energy savings in tighter homes. So it's becoming basically standard practice in a lot of the developed world to use this type of system. So British Columbia and in Canada requires this in the building code to use a balanced ventilation system with heat recovery. It's going to be standard here someday, but really the energy savings really only you only start to realize the energy savings from this because it has a heat recovery core when you start to build very tight homes. So all that being said, it has absolutely the best indoor air quality because it ducts fresh air to everywhere where people actually live. So to the bedrooms, people are breathing fresh, filtered, tempered air. It's quite comfortable, better air quality. That's the best in terms of air quality, absolutely. Supply dominant ventilation systems, I'd say for Victoria, not really typical. For humid climates, a constant dehumidifier is a great idea, but I'll probably leave that one because we don't see that in Victoria much. exhaust dominant ventilation systems, this is how most of the US complies with the building code. They're required to build tight, and required to have some ventilation system. So it's very cheap because they already are required to have a bath fan, for example. Very low running cost, like some of the fans use, like this Panasonic fan that you'll see uses 8 watts. It's like less than a light bulb. It's very low maintenance cost because there's no filters to be changed. If there's dust passing through, it just pushes the dust outside. So it's a very basic measure to reduce condensation risk. So here's, this is not going to be, it's not required anytime soon, unless if you build airtight, you need to have some ventilation. So what that means is for NCC 2022, you can do 10 liters per second of continuous ventilation. These fans, they're available that are quite quiet, really quiet. Basically, when they're ducted well, you can basically not tell that they're even running. And they're very cheap compared to anything else. Like these ones retail for like $250 or less. And you're already required to use a ventilation system there. So in a bath fan for building code. So it's double duty. For intermittent bathroom exhaust, it goes to a boost mode. When you walk in, you flip the light switch on, goes to boost mode, and then when you turn the light off, it goes on a runtime for, say, after a shower, runs for 20 minutes, adjustable by the little settings. There's little dials inside to adjust this. It's a basic continuous whole house system. So removing humidity from the house, from the wettest areas of the house, makes a lot of sense. And that's what most builders use to comply with the basic ventilation requirements in the US, at least. So I'd say, I don't know if I have an example of, so why does it work? Are we going to suffocate if it's only pulling air out? Where does the makeup air come from? Well, it comes from things like gaps. So this is right under my desk here, this PowerPoint under my desk here. Our apartment, remember I said the difference, there's not much difference in terms of build quality, build design between this apartment and the one that was built 100 years ago in Bondi. Same climate. Why do we have condensation there but no condensation here? To me, it's pretty obvious. Actually, you might say, oh, maybe it's the one you have now is lots of fresh air, you might call it fresh air or ventilation. The airtightness of the one in Bondi was about 18, permeability of 18. The permeability of this one is 2.7, so many times more airtight. Why are we not getting condensation here? It's because the building has continuous ventilation drawing air from the bathrooms and the laundry room here, and that's removing all the humidity from where it's being generated. That's why we don't have condensation here. It's a cheap and simple continuously running bath fan. That's why I'm going to be one of the ones signing on for a proposal for change to make continuous ventilation required eventually in Australia. So remember, you got to use a draft stopper on your bath fan because that's required by building code, and you can't duct it into a roof space by NCC 22 and 22. It's got to be ducted to the outside, because you don't want to be dumping the moisture into a cold roof space where it can cause problems. Those are just some basics here. So just a question for you. What do you think? Is adding basic ventilation to a house easy or hard? 1 is really hard, 5 is really easy. What do you think? What do you think? Did I sell you? All right, as I was expecting, we got some people who say, Sean, I won't give you the pleasure of thinking it's too easy. I'd like to hear some of the reasons why you don't think it would be easy to add if all you're talking about in Victoria is a continuous bath fan. I would like to know. Okay, so very cool. Keep replying, but I will move on. So most of you think it's not that hard, and I would be with you. So in summary, we don't need to go over summary. I'll just cut to the question and answer period because we're over time. What are the anonymous attendee says? What are the environmental impacts or embodied energy levels of health hazards of using spray foam throughout your sealed home? So it's very common to use spray foam in the walls of buildings in the US, and it does go through a reaction. In fact, when it's, yeah, it makes nasty chemicals when it's installed. So the people who install it have to wear protective suits, and you need to ventilate it afterwards. But pretty quickly, within a day or two, it's of airing out, it's those chemicals are gone, and this is just shown by indoor air quality monitoring. So if you don't like the idea, there's plenty of other options. So plenty of ways to do it. So what about a bathroom that won't suck the steam, only sucks the air? I am not sure about that, because steam is condensed water vapor, and air includes water vapor as well. So air as a general term means like 78% nitrogen, 21% oxygen, and about 1% water vapor. So if it's taking the air, it's taking the water too. So what about a bathroom that won't suck the steam? Either you have a crappy bath fan that's not pulling enough, or it doesn't have enough makeup air, or the bathroom's actually cold and the water vapor that's in the air is condensing into steam, or the fog that you see is condensation. So it takes time for that to be extracted. If it's let run for long enough, a lot of the steam that gathers when you towel off after a shower, that water vapor in the towels has to go somewhere, and it dries out very slowly. So that's why continuous ventilation is actually better in that case than intermittent ventilation, where you get just a blast of fresh air coming through, drying it out, taking the steam out, but then there's still plenty of water vapor left over after the shower dries out, the towels dry out. That water vapor releases over time and needs to be, I think continuous ventilation is best for handling that continually generated moisture. Is this not working against the effort to be airtight? You're right. It doesn't work against the effort to be airtight. You need to do both at the same time. So some people ask, doesn't it use energy to use ventilation? Yes, it does. And that's a price we have to pay. So in order to get more energy efficient, we need to build more airtight, prevent moisture into wall assemblies, building assemblies. We need to build more airtight. But when you build more airtight, there's less release of moisture due to just wind and things. And so you need to remove that in a more controlled way through ventilation, and that costs energy. You're right, it costs energy. So is air leakage due to tight fittings in NCC 20? Is air leakage due to light fittings in the NCC? A maximum of number of fittings per square meter, types of penetration limited. I don't think so. I don't know. I would imagine that I don't know enough about NatHERS, whether there's lighting power density requirements, like how much lighting can you use? I don't know. I don't know, sorry. But there is definitely not explicit anything about air leakage in the NCC. It's, if you've seen the section 3.12.3 in the NCC 2019, it's very short. So it just says tight fitting and stuff like that. It's totally toothless. Can a ducted refrigerated heater cooler work in place of continuous ventilation? No. So in terms of moisture removal, to remove water vapor, so dehumidifying the air, yes, a lot of builders in the US use ducted an outdoor air intake into a ducted air handler to provide ventilation. It can do that, but yeah, actually that's if what you're talking about is using a ducted component, outdoor air, into a ducted AC, that's extremely common, especially in the southern US, of a way to deal with both ventilation and humidity, because the AC removes the humidity from the outdoor air that comes in, and it cycles on to flush the air in the house out periodically and dehumidifies it. So that's how it's very common there. Is having continuous ventilation not working against the effort to be airtight? It is. It's not working against it, but they have to be done at the same time. Yes, if what you're saying is, does it use energy? Yes, it does. And unfortunately, we have moisture that we need to deal with. And we have pollutants like formaldehyde and things that gather from your IKEA furniture, and like everything is constantly emitting fumes. Printer, just things you buy at the store, rubber seals and things like that are always giving off noxious fumes. And that needs to be gathered. It needs to be removed by continuous ventilation. Does that use energy? Unfortunately, yes, it does. So yeah, will a blower door test change the energy certificate if you already have one? No, I don't think so. I don't think it's going to work like that. Some of those details are yet to be worked out, but I don't think it would do that. It's a great idea if you, one of the first things they can do is just say, why don't you just tell me, I'm not going to do this, but just tell me how good am I doing with my air tightness? Like what were the assumptions used in the energy model? Then you can do a test to say, if the assumption said I was supposed to get 6, but then I got 12, what the heck happened? Like what were the things that I could have done to fix that? An anonymous attendee says, I think there may be a club between electrical code and 7-star when it comes to insulation over lights. Maybe. Conspiracy. Let's see. Let's uncover it, but cover the insulation over the lights. All right. I think that should be where we stop. Thank you for sticking with me.